Let's start off by taking a look at the airplane you'll be flying. Now, the fuselage is the body of the airplane. This is where everything is attached. It's where you load everyone and their luggage. The propeller pulls the airplane through the air. In fact, in aviation's early days, propellers were called air screws because of the way they move through the air like a screw into wood. The engine is attached to the front of the fuselage and provides the power to move the airplane through the air by turning the propeller. The engine also drives the accessories such as the alternator, magnetos, and the vacuum pumps. The wings support the airplane in the air. It's always a good idea to have two wings. They also contain the fuel tanks. Now, the Skyhawk has a high wing, meaning that it is attached on top of the airplane. A high wing has many advantages. The fuel tank sumps are much easier to drain when checking fuel samples. You have much better ground clearance from low obstacles. You have an excellent view down and to the sides. During loading and unloading, you'll really appreciate the shelter the wing provides when it's raining. The wing also provides shade from the sun, both on the ground and in the air. The landing gear is another important part attached to the fuselage. Now, the Skyhawk has what is known as a tricycle landing gear because it has one wheel in the front, that's called the nose wheel, and two main wheels behind it under the middle of the fuselage arranged like a triangle. The nose wheel steers the airplane on the ground and supports the nose of the plane and the engine. The nose wheel does not have a brake and is not as strong as the main wheels. You don't want to have the nose wheel supporting the full weight of the airplane. The nose wheel is connected through springs to the rudder pedals located in the cockpit. If you push the left rudder pedal, the nose wheel turns to the left. Pushing the right rudder pedal turns the nose wheel to the right. The two main wheels are designed to carry the full weight of the airplane by themselves. They are normally the last to leave the ground during takeoff and the first to touch during landing. The brakes are on the main wheels. You control each one individually by pushing on the top of the rudder pedals. And finally, the tail. Or if you really want to impress the folks around the airport, you can call it the empennage, which is really just the back part of the fuselage. Now, this is where the vertical stabilizer and the rudder and the horizontal stabilizer and the elevator are attached to the fuselage. Now, the vertical stabilizer doesn't move. It acts like the tail feathers on an arrow or a dart, and it helps keep the airplane straight during normal flight. You might also think of it acting like a weather vane. The rudder attaches by hinges to the rear of the vertical stabilizer. On many planes like the Skyhawk, the horizontal stabilizer is a part of the structure and doesn't move. It also acts like the tail feathers of an arrow and resists unwanted up or down movement of the tail. The elevator attaches by hinges to the rear or the trailing edge of the horizontal stabilizer.
Now let's take a look at the parts on the wing and tail that move, those parts that let you control the airplane in flight. First is the elevator. It is attached to the horizontal stabilizer at the tail and goes up and down when you move the control wheel back and forth. Now, the elevator controls the nose up or nose down position or attitude of the airplane. Moving the nose up or down is called pitching. And if you want to pitch the airplane so that the nose will go up, you pull back on the control wheel. This raises the elevator into the wind. The up elevator creates an aerodynamic force which moves the tail of the airplane down and the nose up. To pitch the nose back down again, you would move the control wheel forward. This lowers the elevator into the wind and raises the tail. And when the tail goes up, the nose goes down. The ailerons are those movable surfaces near each wingtip. They are also controlled by the control wheel in the cockpit. Now, when you move the control wheel left and right, it alternately moves the ailerons up and down. I know what you're thinking. You're thinking, oh no, I broke the airplane. But no, that's not the case. Really, that's how the airplane was designed. The ailerons are what you use to make the airplane roll into or out of a bank. When you rotate the control wheel to the left aileron moves up and the right aileron moves down. This raises the right wing and lowers the left wing and rolls the airplane into a bank to the left. Now, when you rotate the wheel to the right aileron moves up and the left aileron moves down. This rolls the airplane into a bank to the right. When you bank the airplane, you tilt some of the lift to the side. And it's that sideways lift that makes the airplane turn. So now you know that putting an airplane into a bank makes it turn. And you know that you can use ailerons to put the airplane into a bank. So, what do you use the rudder for? You use the rudder to keep the nose from yawing in the wrong direction when you stick an aileron down into the wind to bank the airplane. Think about what happens when you stick your hand out of your car window. Two things can happen. One, you can get a ticket. More specifically, when you rotate your hand so the palm is at a small angle to the wind, the same force that moves your hand up also moves it back. When an aileron is deflected downward into the wind, the same force that moves the wing up also moves it back, just like your hand. You can use rudder to keep the wing with the down aileron from moving back. The rudder pedals on the floor move the rudder to the left and right. Now, when you step on the left rudder pedal, the rudder moves to the left, and so does the nose of the airplane. This is referred to as yawing the nose to the left. Stepping on the right rudder pedal deflects the rudder to the right and yaws the nose of the airplane to the right. Since the rudder pedals are also connected to the nose wheel, they steer the airplane on the ground when you're taxiing. So, if you're planning on turning the airplane with the wheel on the ground, well, nothing's going to happen and your entire vocabulary is going to be reduced to two words: bad thing. So always steer with the rudder pedals on the ground. Something that most people do not think of as a flight control is the power. It's controlled by the throttle on the lower part of the instrument panel. To increase the power, push the throttle in. You will hear the engine RPM increase, and you can even see it on the tachometer. Now this makes the airplane go faster or climb. Pull the throttle back to decrease the power and RPM. Now you know how the controls of an airplane work. The real trick is making the airplane do what you want it to do.
Let's take a look at the forces on an airplane in flight. First of all, thrust is the force that pulls the airplane through the air. As you increase the throttle, you increase the thrust. Drag, on the other hand, tends to slow the airplane down. In other words, it's the rearward force that opposes thrust. Now, lift is what wants to make the airplane go up. It's the upward force created by the wing as it moves through the air. And finally, weight. As you can guess, weight pulls the airplane towards the earth. Now, let's assume that your Skyhawk is flying along and it's neither changing speed nor direction. It's in what we call unaccelerated flight. In unaccelerated flight, the forces on your plane are in equilibrium. This means that thrust equals drag and lift equals weight, and none of the forces is changing. That's true even if you're climbing or descending, as long as you're flying in a straight line at a constant speed. So if you want the airplane to do something different, you'll have to change one of the forces. Say thrust by changing the power, or lift by changing the angle at which the wing meets the wind. Now let's take a look at a couple of terms. A wing, when viewed from the end, has a definite shape, and we call this shape an airfoil. Well, the curved portion of the airfoil is said to have camber. And if we draw a line from the wing's trailing edge up to its leading edge, that line is the chord line, and it points in the direction the wing is pointing. Now, if our wing is going this way, then the wind will be coming from the opposite direction. We call the wind in relation to the wing the relative wind. Now, the angle between the relative wind and the chord line is called the angle of attack. right here, the angle of attack. And the angle of attack determines how much lift a wing will generate at any time in flight. Now, you as the pilot have control over the angle of attack. Just pull back on the wheel, and the elevator will raise the nose so that the wing meets the air at a greater angle of attack and gets more lift. Push forward on the wheel, and you get less lift. Now let's take a look at a wing in a wind tunnel with smoke going over it. And this is neat because most flights are non-smoking. Now as you increase the angle of attack, the lift gets greater. Earlier we said that lift occurs when wind conforms to the surface of the wing. Well, when that air conforms to the surface, you get a lift. Now, when the angle of attack gets so high that the air can no longer conform to the surface of the wing, the air will not flow smoothly over the surface, and it backfills, burbles, and eddies, and lift is disrupted, and the airplane is said to have stalled. Now, an airplane stalls at a specific angle of attack. The exact angle of attack that the airplane stalls is actually designed into the wing. The critical angle of attack is the angle where the airflow separation begins and that portion of the wing no longer produces lift. An airplane stalls at the same angle of attack regardless of how much weight you have in it. Now let's take a look at an airplane in flight. We stole some yarn from the cat, and while she's at home ripping up the drapes, we taped it to the top of the wing to show you the airflow over the wing. Notice that the wing doesn't suddenly stop flying. A stall progresses slowly over a wing's surface. When the angle of attack gets too large, the air will separate, and that portion of the wing is said to be stalled. To regain that smooth airflow, you just have to reduce the angle of attack by lowering the nose, and the wing is no longer stalled. And you're flying again that easily.
In boats, a rudder is used to turn the boat. In an airplane, the rudder is used to correct for adverse yaw. An airplane is turned by banking the wings to tilt the lift to one side. To make the airplane turn, the pilot rolls the airplane into a bank with ailerons while correcting for adverse yaw with the rudder. It is the bank that actually makes the airplane turn. Now here's why. You can think of lift as being up through the ceiling of the airplane and perpendicular to the wings. When you are in straight and level flight, all the lift is straight up. But if you bank the airplane, you tilt the lift to one side. In a bank, there is now both a vertical component of lift and a horizontal component of lift. It's that horizontal component of lift that makes the airplane turn. The airplane will turn in the direction you bank the wings. When you do have the lift tilted to one side, such as when you're in a bank, the vertical component of the lift is less. The airplane would descend. Earlier, we said that there are 4 forces on an airplane, and they are thrust, drag, lift, and weight. We also said that when an airplane is in a straight and level flight and not accelerating or decelerating, those forces are all in equilibrium. In other words, in straight and level flight, upward forces are equal to downward forces, and forward forces are equal to backward forces. To visualize what is happening when an airplane climbs, imagine you are taxiing your Skyhawk up a steep ramp. Thrust from the propeller is directed slightly upward, and gravity now tries to pull the airplane backward down the ramp as well as toward the center of the earth. You have to increase thrust to compensate for the backward pull of gravity. Now, let's assume that you are flying at a certain speed and you want to climb at that same speed. Since the airplane is in equilibrium, you are going to have to change something to make it do something different. If you want to climb, just pitch the nose of the airplane up and the airplane will begin to climb. When the airplane is in a climb, the path of flight has an upward vertical component. Since gravity now acts along with drag to slow the airplane, more power is required to maintain speed. If you pitch the nose up without adding power, the airplane might climb, but it will lose speed. To maintain speed, simultaneously pitch the nose up and add power. With the added power, the airplane will climb and maintain the previous speed. It is that added or excess power over the power required to fly at level altitude at the same speed that makes the airplane climb. To visualize what is happening when an airplane descends, imagine you are taxiing your Skyhawk down a steep ramp. Gravity now helps to pull the airplane down the ramp as well as toward the center of the Earth. Less thrust is needed because of the free help that you're getting from gravity. Let's suppose you want to begin a descent from straight and level flight, and you pitch the nose of the airplane down. In a descent, the path of flight has a downward vertical component, and gravity helps to pull the airplane forward. So, you must decrease power to descend without increasing speed.